Hello and welcome to this complimentary webinar with the title Discovering the Geometric Suite of Data Analytics Solutions. This webinar is the first in a series of 11 webinars in which we're going to familiarize ourselves with all the elements of the Geometrics Suite, and today the focus is on design of experiments. My name is Lennart Eriksson and I work for Sartorius Stadium Data Analytics Solutions. The roots of Sartorius Stadium Data Analytics Solutions go all the way back to 1987 when Professor Svante Wold and Professor Rolf Karlsson formed a company in northern Sweden called Umetri, which later on became Geometrics, and today we are called Sartorius Stadium Data Analytics Solutions. We are a business solution provider in the fields of advanced data analytics, and our solutions are realized through the so-called Geometrics suite of data analytics solutions, which comprises the following software elements. First of all, we have the MODDE software for design of experiments and quality by design to make sure you get it right from the start. We have the Easy Analytics tool, which is aimed at enabling everyday data decisions in an efficient way. Then we have the flagship Simca for multivariate data analysis, helping you turn data into growth. We have the Simca Online tool, which is using and deploying models built in the Simca offline software in a real-time scenario. And on top of that, we also have the Control Advisor and Active Dashboard layers, which will also be discussed in later webinars in this series. Going back a little bit to who we are, we can say that our mission is to drive growth by enabling our customers to see what others don't, and our vision is to become recognized as the leading data analytics solution provider. Now, going back to the Geometric Suite, we can say that no matter where you are in the value chain of advanced data analytics, the Geometric Suite has capabilities that will help you solve your problem in an optimal way. This suite is the ideal platform to address the early, let's say, reactive questions of descriptive analytics and diagnostic analytics. And here we think of questions such as what happened and why did it happen? But this suite is also the ultimate platform to accomplish the more proactive stages of predictive analytics and prescriptive analytics. And then we are thinking of questions such as what will happen in the future, or how can we make a certain thing happen, or perhaps more importantly, how can we avoid an issue or an upset to happen. Here we have the contents of today's presentation. We are going to discuss design of experiments, and we are using this acronym DOE throughout this presentation. We will discuss why and how DOE is used and where it is used. We will also contrast DOE with the intuitive approach to experimental work, which we call COST, short for consider one separate factor at a time. And then we go back to this better approach and some benefits of DOE. Finally, we are looking at a small tutorial data set, and those of you that have attended other webinars and trainings of the Sartorius Stadium Data Analytics will recognize the tutorial example called Mission Popcorn. There will be a summary and a demo, and also a possibility to ask questions at the end of this presentation. So regardless of where you're working and why you have an interest in DOE, you can say that design of experiments is used to gain knowledge, to increase understanding, and more recently also to estimate proper operating conditions using Monte Carlo simulations. This is also known as the design space estimation approach. You can estimate proper operating conditions of a system, a process, or a product. DOE, you can also say that DOE is applied to many different problem areas, and one of the most important application areas is screening of important factors, which is something you're doing very early on in an investigation. After a screening, you often move over to an optimization stage where you try to optimize and in a very detailed format understand how the different factors that you can regulate influence the different responses or critical quality attribute. Another important application area is minimization of cost and time and material and energy consumption and so on and so forth, making the production more effective. Also, a very important part is robustness testing, which you can see as a final test for ensuring quality before you release a product or a system to the market or the client. Before we discuss what DOE is, we will have a little example of what we call the cost approach. The cost approach is often the intuitive way to experimentation that you will adhere to unless you have been exposed to the ideas and thinkings of DOE. The problem is a small chemical reaction where the goal is to find optimal conditions for the yield. And in this early example, we only have two things that we can vary. It is the volume of the reaction container and the pH. And in the language used in the MODDE software, things that can be varied by the experimenter are called factors. In order to reflect the outcome of changes of the factors, you will then measure some signals reflecting how successful or unsuccessful the experiments are. And in the language used in the MODDE software, the things you are measuring to characterize the outcome of changing the factors, this is the one or more responses. And in this case, we have one single response, which is the yield of the desired product. So in the cost approach, what you would do would be first to vary just one of the factors and lock the other one at a constant setting. So in this example, pH is fixed at pH equal 3, and the volume of the reaction container is changed between a low setting of 500 milliliter and a high setting of 700 milliliter. And here we see in this little table the yield that was obtained when changing the volume from 500 to 700 milliliters. In the scatter plot to the right, we have plotted the measured yield against the change in the reaction volume, and it doesn't take long for us to find out that the best volume is located at 550 milliliters. So in the second step, what will then happen is that you will fix the volume at 550 and start to change the second factor. In this second experimental series, the pH is then investigated between 2.5 and 5.0, and you can see the measured yields listed in the table and plotted here in the scatter graph, the yield against pH. And we then make the conclusion that the optimal pH is around 4.5. So the optimal combination of volume would be 550 and pH would be 4.5. Now, if we take a little more of a bird's eye perspective and look at the real experimental map, what have we done? Well, the first experimental series, we were changing, you can say, in the horizontal direction. Volume is here. We were changing from left to right, and we found out that 550 was the optimal setting for volume. Then in the second experimental series, you can say we allowed ourselves to move from bottom to top in this scatter plot. And after a while, we found out that the best yield was at experiment number 10. The problem here is that we are not really sure whether the experimental point number 10 is truly the best one. The risk is that we perceive that we have reached an optimum without that necessarily being the case. And another thing we would like to question is also how many experiments that we have used. Have we used the optimal number of runs or experiments? Zooming out and picturing what we have done in the real map, we can see that we have only been exploiting a very, very small part of the entire experimental volume. The true relationship between pH and volume is represented by this so-called contour plot, and we can see that now red laser pointer and red here for the optimum is perhaps not the optimal combination, but if I move around a little, you will see this little dot here. The optimal value would be up here somewhere in the top right corner. So the problem here with the cost approach is that we can get very different implications if we choose different other starting points. So we perceive that the optimum has found, and the other and perhaps more problematic thing is that we don't have an understanding of how to continue to do experiments in order to get even higher yields. Instead, what we suggest is to make use of the DOE approach and build a map in a much better way. So design of experiments in the case of two factors would mean that we would arrange the experiments in a fashion like this, so that we would have at least 4 experiments defining the corners of a rectangle. And these 4 corners can then be optimally supplemented by a couple of points representing the variation in the interior part of the experimental design. The important thing here is that when we start to evaluate the results, we will obtain very valuable information about the direction in which to move for improving the result. We will understand that we should reposition the experimental plan according to the dashed arrow. And DOE is of course not only locked to just 2 factors, it can be applied to 3 and 4 and many factors. And if we take the step from 2 to 3 factors, the experimental protocol will start to define a cube rather than a rectangle. So the factorial points will be the corners of the cube, and then you can do a couple of experiments in the inner part of the design. In the lower part of this slide, we also see an alternative experimental protocol where there are a couple of more points, the green points that have been added, and this configuration of experiments is then used when we want to extract very detailed information about the relationships between the factors and the responses. But we will not go into those details in this early stage of this webinar. The important point is that regardless of whether we want a superficial investigation with this upper design or a more detailed investigation with this lower design, DOE is about creating an entity of experiments that work together in a very good way to map the interesting region. So with DOE, we will prepare a set of experiments that are optimally placed in order to bring back as much information as possible about how the factors are influencing the responses. And depending on which experimental protocol we are selecting, the upper one or the lower one, we will have support for different types of regression models. Can sometimes be able to estimate what we call a linear model, sometimes we can have an interaction model, and sometimes we can have a quadratic model. So the selected experimental plan will support a certain model where there are some model terms included in the model, and what we do in the data analysis stage is to find the coefficients of this model. The pattern of the coefficients will then dictate the shape of the response contour plot or response surface plot that we can then produce and start to interpret things and make conclusions about what to do next. So the benefits of DOE is that it is an organized approach which connects experiments in a logical, rational manner. We can estimate interactions between factors if we want to, and we can contrast the size of the interactions with the so-called main effects. Overall, we can show that we get more precise information about how the factors influences the responses in fewer experiments compared with the cost approach. And perhaps the most important argument why adhering to DOE over cost is this support for decision making, that we can map the system, we can produce these very reliable response contour plots. With this little introduction in mind, we will now move into this demo case that is called Mission Popcorn, with the subtitle Making DOE Understandable to Kids. The whole background to this little endeavor goes back to the summer of 2006, where the presenter and his two sons, at that time aged 10 and 7, were visiting the famous amusement park Legoland in Billund, Denmark. And one afternoon we had some very nicely tasting cotton candy, and the kids were very, very pleased with that. And a couple of hours later we also tried out the cotton candy, but it was a very distasteful popcorn. It was a burnt bag of popcorn with an unpleasant odor. So when sitting in the hotel room in the evening and complaining about the bad popcorn, we decided that once back at home we would do a popcorn experiment and really try to optimize the popcorn to get it well tasting and very fluffy. So when we were back, you can say that back at home, the practical objective was to explain to kids what DOE means using an everyday problem, how to get good popcorn from the microwave. When you're running DOE using the MODDE software, you have to select the so-called experimental objective that can either be screening or optimization. And there is another alternative notation in the software for optimization called RSM, Response Surface Modeling. The first step in the MODDE software and in any DOE investigation consists of defining the factors. These are the things that we could change. And in our Mission Popcorn example, there were two factors. It was the time spent in the microwave oven and the power of the oven, both adjustable on a continuous scale. So after some range finding experiments, it was decided that time should be varied between you can say 2 minutes and 50 seconds up to 3.5 minutes, and that the power of the microwave oven would go from 600 watts up to the performance restriction, you can say 800 watts. And here you see what it looks like in the MODDE software when defining the factors. In the next stage, you're defining what you can measure to characterize the experimental runs. These are the so-called responses. And also here we had two variables, kernels and taste. Kernels, that is simply the number of unpopped kernels remaining after popping a bag of popcorn and having eaten up all the popcorn. And taste is then how the three persons involved in this investigation expressed his liking on a 5-level scale, running from 1, which would be very bad taste, to 5, which would be the ideal dream taste. And the final response value is then the sum across the three persons that tested the popcorn. The little brother was too young to understand an average, so we were using the sum instead. After entering these inputs, factors and responses into the MODDE and selecting optimization, MODDE will propose a very good experimental plan, in this case the central composite face-centered optimization design. This is a design that by default has 11 experiments in the MODDE software, but in this case we had only access to a bag of 10 pack of microwave popcorn, so we were dropping one of the so-called center points, so we went down from 11 to 10 experiments, and here we see the 10 combinations, and combination 9 and 10 are then preserved, forming so-called replicates. We also see the number of unpopped kernels and the taste, and what we now want to do with the data analysis is to see if there is any relationship between how the time and power is changed and if it can correlate and predict the number of unpopped kernels and the taste that was judged to be the case. Before we go into the data analysis, we also go through the workflow a little bit. And one important thing is to always look at the raw data before doing any data analytics. And here we see how you can use the scatter plot representation in the MODDE 12 software. So we have plotted power and time. We see the 9 combinations, and then we have done the center point twice. The leftmost plot is for the taste response, and we are then using a color coding running from blue to red. So a blue color would be a low numerical value, a low number of a low number for the taste, up to a red value, which would be a very high numerical value, in this case for the taste. In the right-hand part, we see the same plot for kernels, color-coded then, and we can see that an very interesting thing would be centered around the middle section, actually, because here we combine a low value of kernels and a high value of taste. So the center point region looks promising just by looking at the data without even doing any statistical analysis. Inside the MODDE 12 software, we have something called the Analysis Wizard, and the Analysis Wizard is a guided workflow that will help you to go through the most critical and essential steps in the data analysis and in the correct order. One of the plots that is a part of this Analysis Wizard is the replicate plot, and the replicate plot will show us how much the variation in the replicates will be in relation to the spread across all the measurements in the experimental plan. And what we are looking for and hoping for is that the variation among the replicates will always be much smaller than the variability across all the other experiments. We would not want to see a situation where the spread in the replicates is almost in the same order of magnitude as the spread across all experiments, because then we would have a real replication problem and poor control over our experiments. In this case, we have very small replicate variability, and we would use sort of a happy smiley here to document how we feel when we see these nice plots. Another plot that is part of the Analysis Wizard is the so-called Summary of Fit plot that contains 4 model performance statistics. We will get 4 bars for each model. We have one set of statistics here and the other quartet of statistics here for kernels and taste. And without going into any details, what we can say and what is important to remember is that we would like these 4 bars to be as high as possible, and the closer to 1.0 the better. And the really critical parameter is the dark blue bar, which is indicating the predictive power of the model. So in this case, we have 2 very strong models for both responses, meaning that there is a strong influence of the 2 factors, time and power, on the 2 responses, kernel and taste. Another plot that is part of this Analysis Wizard is the so-called regression coefficient plot, which we can use for model interpretation. And in this case, because we have selected the design we have a predetermined set of coefficients in the model. This is a quadratic model, so the predetermined model will have a linear term for each factor, a quadratic term for each factor, and the 2-factor interaction. And what we have done in the data analysis phase has been to ascribe numbers to these terms, calculating the coefficients and their uncertainties. We have the t-bars here, the error bars, they correspond to 95% confidence intervals. So what we see here is that to minimize the number of kernels, both time and power should be on the high setting. Time and power also have a similar influence on taste, so adjusting both factors on a lower value in this case corresponds to increasing the taste. Another way to interpret the model and visualize the consequences of the models is to use what we call response contour plots. And here we are seeing how when we're changing power and time, the kernel response is predicted to change. And in the right-hand plot, we have the similar thing for taste. And it doesn't take long for us to see that there seems to be an optimal point for the taste around 180 seconds, a little more than that, and 655, 660 watts. The optimal combination is 182 seconds and power of 657. That gives the highest taste. The problem is that that coordinate is in conflict with regards to the lowest possible number of kernels. We would like to be up in this region to find a lower value for kernels. So these responses are in conflict. Now, in order to arrive at a possible workable solution, we have to define what are the goals, what are the specifications for these two responses. So after a while, we went back, the two sons and their little older father, and sat down together to figure out what we really want. And now regarding the taste, regarding the number of unpopped kernels, you have to envision that we had this bag of popcorn. It was divided in 3 streams, 1 bowl per person. And I was then asking, after you have eaten this bowl of popcorn, how many unpopped kernels would it be okay for you to have left in the bowl? And after a while, they sort of mentioned 20 and 10 and 15 and different numbers. But after a while, they agreed on 20 and both nodded in a way so to sanction that number. So 20 times 3 kernels would then be a total of 60. And that is in fact quite reasonable setting because we opened another couple of unpopped bags of microwave popcorn and counted the number of unpopped kernels, and it ranged between 575 and 650 or so. So having an upper maximum setting of 60 is about 10% unpopped kernels. Regarding the taste, we all agree that if each person scored a 3 on the 5-level scale, that would be an acceptable taste, and therefore 9 would be a fully acceptable taste. So going back to the responses definition, we then set up the following specifications. The number of unpopped kernels would of course be minimized, and the ideal value would be 0. That would be the target value. If the target value is not within reach, we should definitely be below the upper maximum setting of 60. The taste is not going to be minimized, but going to be maximized and driven towards the target setting of 15. If 15 cannot be reached, we should at least be above the minimum level of 9. Now with these specifications, we can now go back to the two plots that we were looking at on the foregoing slide. And you can see now that these settings are also indicated by a little they are emphasized by a slightly widened or thickened line thickness of these black lines. Here we have the maximum of 60 for the number of kernels, and the target of 0 is down here. Whereas for the taste, only the minimum setting is relevant, and here we have 9, and anything down here is then acceptable. In the MODDE software, we can then combine these two contour plots, and instead of color coding according to the predicted levels of the responses, we color code according to how many specifications of the responses are fulfilled. And if there is a region in this so-called sweet spot plot, which is then an overlay of the contour plots, where we have a green color, then we know we have a sweet spot, because then both, in this case, both specifications are met. In the case that only one specification is met, then we have a blue color. And you can see here in the sweet spot plot that there are 2 lines demarcating the position and size of the sweet spot. Here we have the minimum setting of taste dictating the border, and here we have the other border, so to say, arising from the max setting for kernels. What we can then do in DOE is to take another step by starting to estimate how stable this system is. What about small uncertainties in the factors? What about model uncertainties? What about different uncertainty intervals and so on and so forth? How stable is it? And then we take the step from what we call the sweet spot plot over to what we call the design space plot. In the design space plot, we have considered a number of different uncertainties, and we are then, instead of just indicating the size of the sweet spot, we are indicating level curves corresponding to the probability of failure. What is the risk of failing to comply with the specifications for kernel and taste? And we are then using by default an acceptable risk setting of 1% probability of failure. And if we have 1% or smaller, we have a green color. Between 1 and 2% risk of failure, we have a yellowish color, and then we gradually go up to a more and more intensely red color. So we can see that the safe area suggested by the design space plot is considerably smaller than the corresponding region indicated by the sweet spot plot. In addition to that, the toolset in MODDE will also indicate a so-called recommended setting for running this system, where we have maximum borders to the maximum distances to the borders or margins to the borders of the design space, and that coordinate we call a set point, and its position is indicated by the crosshairs. The final point that we were selecting was 700 watts and 190 seconds, which is very close to the tip of the 0.1 probability of failure line. And we are still today, many years later, using this setting. I will come back to that in a slide or two. So with this design space explorer plot, inside the MODDE 12 software, we are indicating the extent of the design space, and we also have a dotted frame which corresponds to the largest, you can say, regular geometrical structure that can be inserted into the often highly irregular design space volume. So the design space can be a highly irregular volume delimited by factor precision, model errors, and specifications, and of course also the number of factors and responses that are involved in a QBD investigation. And you can always have a full account using something called a Design Explorer list. And here we have then the design space hypercube, which represents the largest possible geometrical structure that you can insert into the irregular design space. More about these tools and how they are used in quality by design and robust optimization will be discussed in the next webinar in this series in part 2, which has the subtitle Robust Optimization. So looking at the final outcome, the end result of the Mission Popcorn investigation, as I told you in the foregoing slide, we were able to find out a suitable combination of 190 seconds and power 700 watts. And today, almost 12 years later, we are still using this combination with great satisfaction. It produces very well-tasting popcorn without any undesirable side effects. And it must have been a very good diet, you can say, because the boys are now 190 centimeters, both of them. So seemed to have been a really nutritious thing. The last thing said with a great smile on my face. Now this brings us over to the demonstration, and we're now going over to the MODDE 12 software to demonstrate this Mission Popcorn dataset. Whenever we are defining a new investigation, we can use the so-called design wizard. And when we click on the design wizard, the first stage corresponds to defining the factors. And we can double click here and start to define the factors. Minimum input information is a name. The unit is optional. The first factor is time, but we have to define or supply the low and the high setting, which in this case is 170 to 210 seconds. We can then add the second factor, which is power, which is measured in watts. We have the low level of 600 and the high level of 800 watts. We don't have more than two factors, so we click OK. We can then click Next in the design wizard, and now we are at the stage where we define the responses. The first response was kernels, and in this case the target was 0 and the maximum tolerable setting was 60. We want to be below 60. We also add the second response, which is taste. In this case the target was 15, but if we could not reach 15, we should definitely be above a minimum level of 9. We can now say OK and proceed to the next stage. And now we have to instruct the MODDE software whether we want to do a screening or an optimization, and we select optimization. MODDE will now sense the number of factors that we have defined, their nature, if they are continuous or qualitative or multi-level or whatever, and then propose a good design that has a high potential of solving our problem. Often MODDE has both a first and a second recommendation, and whenever you have that possibility, we recommend you go by these recommendations. In this case, the CCF is short for Central Composite Face Center Design. It has 8 runs and 3 replicated center points. So we will drop 1 center point to get down to a total of 10 runs. I click finish and voila, here we have the experimental plan. I will just go to Excel and fetch the response measurement so we can continue. And now you can say we have completed all the stages of the so-called design wizard. And now you see that a second wizard right next to it, the so-called analysis wizard, have become active. And this is the tool that I told you was to be interpreted as a guided workflow. And when you open up or launch the analysis advisor, I will maximize or enlarge so you see something, you will then see the different plots according to a fixed order. And first of all, you will be starting with a replicate plot for the first response that you define, which is kernel, and you see we have a small replicate error, which is good. Another plot which I did not show you in the PowerPoint part is the histogram plot, where you're looking into if you have skewed response distributions and so on and so forth. And what to do in different circumstances is also available in terms of information in the so-called info pane. In this case, we are having just 10 experiments, so discerning the contours of a distribution is a bit diffuse or a bit difficult, so we are not going to overemphasize the importance of this histogram. At the next stage, you are looking at the four performance model performance indicators, which in short are the explained variance, the predicted variance, model validity, and the reproducibility. And the higher the better, the closer to 1. The closer to 1, the higher the better, and in this case we have a very good model. We can then look at the model in terms of the coefficients. Another supplementary diagnostic tool is the so-called normal probability plot of residuals, where we are looking at deviations between the measured value and the estimations made by the model. In this case, we have so strong model, we have a very high predictivity of close to 85%, so this experiment is not alarming at all. If we would have much weaker modeling statistics, then we could have used these red limits, the warning or action limits located at minus and plus 4 standard deviations as indicators of potential outliers. So it was this deviation for experiment 7 we were looking at in the previous plot, and as you can see, it's not that dramatic, and that is also what we could judge from the strong modeling statistics. This is the last plot in the guided workflow, and we then move over to the second response, and we sort of rewind the tape and start all over again from scratch with the replicate plot, but for the second response. So we have the replicates for taste, which is good. We have an approximately normal distribution, which is good. We have very strong modeling statistics. We see the model, we look at the residuals, and finally we have the observed versus predicted. And then when we click finish, we are outside the wizard, and we can now move on to other tools under the diagnostics and interpretation group. For instance, the contour plot. The contour plot will then display how changes in time and power will predict various settings of the responses, various levels of the responses. And if you only see one response, you have a little selection field up here in the top right-hand part of the MODDE software, where you can kick alive both responses in this case. And here you're seeing the response contour plots that I was talking about. You can also create the sweet spot plot, and then that would be the sort of overlay interpretation or representation
of the two contour plots. And as I told you, if you have a green area in this plot, that is what we would call or use the notation sweet spot region for. Finally, you can move into these uncertainty disturbance-based Monte Carlo simulations to try to estimate how sensitive the response is to small fluctuations in the factors and how sensitive the overall result is to different sources of uncertainties. I am now running on a relatively low resolution, so the results should be available within the minute or so, hopefully, and we can then display a design space plot. Depending on how you're configuring these calculations, they can easily last up to the hour scale, particularly if you have 4 or 5 factors. The most critical setting in these studies is what we call the resolution, and the resolution is how many intervals you are dividing each factor into. You can run on a resolution setting from 8 up to 64, and when this converges, you will see the corresponding so-called design space plot. I think we will stop here and change the I think I was running on a higher resolution than I was thinking I did. I changed to a slightly lower resolution. We can go perhaps also to a resolution of 32 even. What happens when you're doing these early stage range finding type of calculations and running on a low resolution is that the contour lines will have a little rugged appearance, and you can see here that the sort of general structure that I presented in the PowerPoint part is still discernible, and the ruggedness of these lines comes from the fact that we're running on a low resolution. But there is no doubt about the fact that there is a region, the green color, where there is a very small risk of failing to comply with these specifications. It's less than 1% risk.
So, and we are now back in the PowerPoint part, just once again reiterating the things we were looking at in the example, in the demo, and here we see the high resolution version of the final plot that we had in the demonstration session. Summing up DOE, we can say that DOE results in a set of experiments in which all factors are varied systematically and independently in an informationally optimal manner. And the number and the type of factors and the regression model that we select will specify which experiments are needed. And the MODDE software will then come up with a proposed experimental plan that has very, very good probabilities of solving our problem in an optimal way. As I briefly alluded to in the beginning of this presentation, design of experiments is used for 3 primary experimental objectives that are listed here: screening, optimization, and robustness testing. And that is also, you can say, going from top to bottom, corresponding to the chronological order in which you are doing DOE and increasing awareness and understanding of your system. So in the screening, we are looking at many factors, and we want to sort out the most important ones and also find out the appropriate numerical ranges in which to investigate them. In optimization, we want to extract much more detailed understanding of how the factors influence the responses. And in the robustness testing, we are addressing how sensitive things are around an optimal setting, which responses are sensitive to small changes in the factors, they would then not be robust, and which factors are not or are insensitive to small changes in the factors, these would be the robust ones. And for the non-robust and sensitive responses, equally important questions are then to find out how to proceed in order to go from a non-robust system to a robust system, how to sharpen the tolerances on the factors so that in the end you can actually claim a robust system. If you're comparing DOE with the intuitive approach to experimental work, the cost approach, we can say that there are a number of tangible benefits coming out with DOE. First one is that factor interactions are estimable and plottable, and that because we have spread the experiments in a very informationally optimal manner, we can produce extremely reliable maps of the system and make concrete decisions about what to do next. We are also very much emphasizing that we should not just mechanically look at the models, we should interpret the models, and we should consider the scene effects and the noise in terms of the coefficient plots. We can separate and estimate effects from the noise using the DOE. And finally, it also lays the ground for this probability analysis, the risk of failure analysis, that is the entry point into robust optimization and quality by design, which we will discuss more in the next webinar. A little recap of what we started off with. We mentioned that the geometric suite of data analytics solutions is there to help you as a users to see what others can't see, to see what others don't see. And we have gone over the different softwares that are part of or making up this geometric suite, and today we have been looking into the MODDE software, and also in the second webinar in this series we are going to look more into the data analytical powers of MODDE. And gradually, as we move on through the webinars in this series, we will be able to have a walkthrough of all the different software elements making up the geometric suite. Removing the names of the software, we can say that with this suite of data analytics solutions, we have a very powerful way of addressing all these different data analytical questions: the descriptive question, the diagnostic question, the predictive question, and the prescriptive question, trying to sort out how things should be changed in order to improve the situation. So from the Sartorius Stedham data analytics solutions side, using the geometric suite, what we would like to help our clients and customers to do is to look into their databases, do data analytics on their historical data and on their upcoming data, do data mining, find the valuable nuggets or the golden nuggets in their data, understand how to capitalize on those. In short, understand how to change a little and thereby grow a lot. And having said that, I would like to thank you all for attending this webinar, and I hope to see you on board in the coming webinars in this discovery series of the geometric suite of data analytics solutions. Thank you so much for your time and attention.